Hi everyone, this is Han who works for the IREE team. And our team gave talks about CPU detailing and GPU detailing in the past couple years. And they are more about the code generation concept, like layouts, instructions, microkernels, performance, etc. Today, I will be talking about how we set up the detailing idea and how the optimizations are unlocked in the IREE compiler. So before we jump into the main topic, I'm going to share what IREE does and how we get the detailing idea first. So IREE is a MLIR-based compiler for ML programs. The ML workloads from various front ends can be imported into MLIR. The HLO, TOSA, and Torch MLIR dialects are just high-level input dialects. Most of the optimization does not happen at this level. The first thing IREE does is converting all of them to MLIR core dialects that are the real input dialects for the IREE compiler. The heaviest dialect we use in IREE is the lineage dialect because it can structurally capture most of the computations like element-wise operations, math-mode, convolutions, etc. All of the input dialects are defined in MLIR core except the lineage X dialect. Then IREE compiles the model written in lineage ops into some artifacts and execute on target devices. And IREE's programming model is host device programming model. The terminology used here comes from classic accelerators world. There are hosts and devices. What the IREE compiler does is partitioning your program into host codes and device codes. The host codes schedules the work that needs to be done, and the device code that actually execute the work. So let's unpack more context from IREE compilation. Once front ends convert the ML programs into lineage and some other dialects that you need to represent your program, we get into the start point of the IREE compiler. At this level, we have similar to opt. We have the program level canonicalization patterns, and they do some basic element-wise fusion. You can do things like propagation, transpose propagation, reshape propagations, everything that you need to do to effectively get your program into a better state for the rest of compilation. And then we go to the dispatch creation phase, and IREE defines the flow dialects for the work. The purpose is to take the input program and partition it into several dispatches. The constraints of what goes into dispatch are very similar to what you would expect in a GPU kernel. You expect that a dispatch is being executed by many workers. On CPU's land, it maps to threads. On GPU's land, it maps to work groups. And the workers do not synchronize with each other in the middle. Once we start a dispatch, there are a bunch of workers that are going to execute the work in parallel and synchronize at the end of dispatch. So we also capture the dependence between dispatches. We wrap them into some flow dispatch workgroup ops. Workgroup op takes some operands and produces result tensors, and where the result use captures the dependence between dispatches at SSA level. So you can think that a program becomes a set of functions, and how we call the functions in the program is captured in this phase. Then in the string phase, since we have the dependence between the dispatches, IREE tries to create different strings of work that could be executed with minimum synchronization. This is also where we're getting into memory allocation. The scheduling and memory allocations need to be modeled altogether. At this level, you can schedule a group of dispatches to be executed on either A device, B device, or C device. How to handle the data flow is important at this stage. Even if we only have a single device, we still need to teach the device about the memory allocation. And then we go to the how dialect. Each target implements the hardware abstraction layers. What the how dialect is doing is taking your host side code and generate codes into the how that each target implements. This is where it sets out the actual command buffers. And on the other hand, we also do code generation for device code. So each dispatch that was created in the flow dialect goes through string dialect without being modified and get it in how dialect each backend gets the dispatch with the computation that it needs to generate code for. So at the end, we get the VNF file, which is the final artifact from the IREE compiler that includes host code and device code. And with this layering, we design a retargetable ML compiler so that if there is a new CPU coming with the same target implementation, you just need to build a codegen for it, and everything should be working automatically. And what is popular in the ML compiler is delegating primitives to libraries. The models are imported into a graph compiler. Then we may do some pattern matching and delegate them to execution library, which calls performance kernels. And it is true that usually libraries, or say handwritten kernels, can have very, very good performance because they know the target ISA details and have better control for instruction scheduling, etc. However, the solution could be suboptimal in terms of the whole program performance. There are some mostly design caveats. It usually results in a trade-off scalability and performance. And it may be easy to write a performance kernel today, but it may not be easy to reuse the kernels, especially when fusion is involved. So what we want to learn from the library approach is how to integrate such idea into a retargetable compiler concept. The keys to the performance are about instruction scheduling and memory access improvements. We want to target the right instructions, have good scheduling to avoid stalls, and optimize register usage as much as possible without scaling. We have discovered that almost for any architecture, you want the input data to be in a particular layout for good performance. That allows you to access data through the cache hierarchy efficiently and do the computation with very less latency. In most of the library approach, typically we would perform the relayout inside a kernel. There is a cost of doing the relayout things, and you have to amortize the cost. However, as the IREE is a compiler which can seize the whole program, there are many opportunities to remove the relayout overhead that may be propagated, fused into other operations, or be constantly evaluated when the source is from wait. So introducing the layout transformation is not hard in itself. What is hard is making that fit in the progressive lowering design of a retargetable compiler. The solution we have in IREE is using Tensor encodings. So from the source, we have math modes in a ML program. In the either global optimization phase or dispatch creation phase, we add attributes to the tensor types that encodes the role of that tensor and whatever needed information. At the string level, we convert the verbose encodings into serialized encodings and use the information to lower the string ops. For example, IREE defines the string tensor size of op that queries the total storage size for a tensor and can use it to issue buffer allocation in the host compilation. Later on, the codegen materializes the encoding ops into physical operations and types. For example, in our CPU backend, we lower the encodings ops into the packing ops and the nudge and P4D ops. The configuration is different based on the CPU features. Yeah. So, however, you may have a question like how does string interpret the encodings? Like what we showed in the verbose encodings, which is a tensor encoding for a math mode left-hand side operand. It encodes the element types that helps you make the decision for target intrinsic. It also encodes the user indexing maps, so you're able to handle the transposition variance during lowering. Furthermore, it can encode iteration sizes for each dimension, so you can do ninja optimization when there are narrow metrics, especially for the mathematical cases. So the encoding is very verbose, and the string is not able to interpret such tensor encoding. And the answer we have is using the encoding resolvers that are attached to executable targets. And executable target describes the target features, and we can attach whatever target information to the dictionary attribute. String dialect does not need to know all the details, but it needs to know the target devices. That's why we define the affinity in the string tensor ops, which represents devices. Otherwise, it's not able to perform scheduling optimizations and memory allocations for data flow between dispatches. With our string affinity analysis and dialect interface mechanism, we are able to retrieve the potential encoding resolvers for tensor ops and resolve the verbose encodings. And the encoding resolvers implements a couple of interfaces to help lowering. In other words, it translates the verbose encodings for the string tensor ops. So after we plunge through the encoding work in the IREE compiler software stack, we identified that there are 3 states for an encoding, and we also introduced 3 interfaces to help the lowering and describe the encoding properties. So starting with verbose encoding, we use the layout resolver attribute interface to resolve verbose encodings into serialized encodings. One of the key interface methods is getLayout, which takes rank tensor type as input and returns a new attribute that represents a serialized layout. Then we define the serializable attribute interface that describes the properties for serialized encodings. Once an encoding is serialized, it is expected to have enough information for string tensor ops lowering. And one of the key interface methods is calculate storage sizes in bytes, which takes the tensor type and the dynamic dimensions, and it returns the storage size in bytes for the input type. For the last step, we define the layout materializer attribute interface that brings the encodings into physical operations and types. It is mainly used in cogent phase. In the past, we implemented different encoding materialization passes for different backends. After we learn more about encodings, we have better abstractions for the encodings, and we create the interface for the lowering. All the lowering are developed through the interfaces, which means that people can create their own encoding attributes and resolvers to plug their work into IREE as long as they implement the interfaces. So looking at a concrete example here, after retrieving the potential encoding resolver, we can specialize the encodings for tensor size of op. For example, the left-hand side is the original verbose encodings, and it becomes the serialized encoding after specialization. To be more specific, we use the getLayout method from the interface to achieve the conversion. The serialized layout can be well-known layouts like padding, or the customized layout like encoding info. For customized layout, it is usually wrapped by the encoding resolver. In other words, the resolver also implements the serializable attribute interface. Because the layout is defined by them, so it is their responsibility to interpret the layout. And this is why the encoding info is wrapped within the encoding resolver in this example. And this encoding info maps to a lineage pack-off. After the encoding specialization, now all the encodings are serializable. It runs a encode host tensor path that transforms the tensor-like object into encoding erased asynchronous ops. For example, it casts the left-hand side encoding into serializable attribute interface and use the interface method to calculate the final storage size in bytes for the tensor. And so this is how we abstract the encodings and introduce the interfaces. In summary, there are 2 categories for encodings. One is encoding type attribute that is expected to be attached on encoding types. The other is encoding resolver that is for resolving and transforming encoding type attributes. There are 3 states of the encodings. We start with verbose encodings, lower them to serialized encodings, and materialize them into physical operations and types. And to achieve the lowering, we introduce 3 interfaces. And encoding resolver implements the interfaces that transform the encoding type attributes between the states. The layout resolver attribute interface resolves verbose encodings into serialized encodings. The serializable attribute interface describes the encoding properties that have enough information for further lowering. The layout materializer attribute interface provides a set of methods to materialize encodings into physical operation types, etc. And now we're going to talk about what optimizations are unlocked by the encoding work. Some of them are already enabled in the IREE compiler, and some of them are still under development. So as IREE is a retargetable compiler, it can see the whole program and fills the encoding ops with producers easily and enable hoisting and constant evaluation. For example, after we introduce the encodings to Linux Maximus through the set encoding ops, we're able to hoist those ops outside dispatch region and either fuse them with producers or wrap them in their own dispatches. In this example, we fuse the left-hand side encoding op with a producer, and we create a single dispatch for the right-hand side encoding op because the source is from weights. From our experience, the encoding fusion amortizes the relayout overheads. Sometimes it only reduces some overheads because it's not magic, and it depends on how you generate the code and fuse them with other computation ops. The right-hand side example shows that we can hoist such dispatch to initializers. If the weights are compile time known, we can kick in the const evaluation, which hides the relayout overheads in compile time. If they are not compile time known, during the execution, we can firstly relay out the weights in initialization phase, and then start the actual execution or inference later on. And the hoisting is enabled in the IREE compiler, and the const evaluation is partially enabled. Yeah. And furthermore, we can do encoding propagation globally, which is very similar to data layout propagation. For single device cases, we have experimented early encoding materialization that enables the data layout propagation globally. However, it does not fit the multi-device story, as there could be different layouts in multi-device, and you're not able to do device analysis at global optimization phase. Thus, what we're working on is encoding propagation. In this example, we try to propagate the encodings across the collapse ship op and fuse it with the producers. It should be a valid propagation because the total dimensions are extended after propagation, and we don't lose any information in the SSA chain. Yeah. So a more interesting topic is how to make it work with multi-device concept. The IREE team has been pushing this area, including the homogeneous computing and heterogeneous computing. IREE defines those device transfer ops to model what the target device is for a portion of the model. As encodings are just virtual layouts after specialization, we already have enough information if the input program is valid. And here is a demo, shows how data tiling works with heterogeneous computing. There are more work to do if layout transfer is required, but we already have some proof of concept for that. We're not going to unpack the context since it's not within the scope of this presentation. And last, as you can see, the encodings are not data tiling specifics. We started work with the encodings, and today we have better abstraction for the encodings. Now IREE has the ability to spatialize storage size based on logical tensor dimensions with target-specific requirements. Furthermore, the encoding work is a plus, but not a requirement in IREE. What I've been pushing forward is ensuring that identity layout works when a backend does not need the encoding hints. We also have other path-based encoding strategy in IREE, and it is not data tiling specific. And today, our team has been developing the split K and string K ideas in IREE compiler concept, and they can use the encoding work. Yeah. And we haven't finished all the work, and here are some future encoding work for data tiling. And we are trying to move the set encoding path from global optimization phase to dispatch creation phase that enables the consumer fusion for CPUs. And it also requires us moving the const evaluation techniques down after the phase. And the encoding propagation is also under development as well as multi-device. And yeah, that's all I had for today. And thanks for your time.
Thank you so much. Any questions?
Yeah, I was wondering, is an IREE layout conceptually similar to a memref layout map?
Can you use that again?
Is an IREE layout, is it similar to a layout map on a memref type in MLIR? You know, the memref type, you can specify, it has like dimensions. The memref has dimension, then you can also say it has like offset and strides. So yeah. I'm wondering if the IREE layout kind of solves the similar problem.
So I think at the coding phase, we're heavily using the memref dialects. So that's the truth, that's the fact. In the host compilation, you don't really care about the, what you care is about like how you allocate a buffer, you provide the sizes, offsets, and strides for the pointer. It's basically similar to C pointer like stuff, and call the functions. Yeah, so as host compilation phase, we don't care about memref that much, but at coding phase, you care that much because like you need to use that to represent the memref types after tiling, distribution, vectorization, and whatever stuff.
Okay, so but when you run on the device, I think probably your data must be in like certain layout for the matmul units and stuff like that. Is that what the layouts try to achieve?
So when you execute it in terms of the layouts for the device, who introduced the relayout is also the backend. So it's more like you have a source buffer, maybe the weight, you have the destination buffer, and the device can propagate the storage size and do the relayouts, perform those relayout ops itself. So when you come to the actual maximal kernels or whatever other kernels, this is the layout that expected by the device, the target. Mm-hmm. And typically it's a pointer plus some size, and it could be a stride tensor if you need a stride, yeah. Mm-hmm. But typically how I see this problem is more like try to see what you would do it in C code. Like most of the time you just provide pointers, the total size, the strides, and the offset. Yeah.
Mm-hmm. Okay, thanks.
Any others? All right, well, thank you so much. We're gonna let's give him a warm round of applause, please.